Let's talk about section 8.1, estimating the population mean, where the standard deviation of the population is actually known. So understand that there's going to be a few different sections here that we are going to talk about estimating the population means. And again, this is going to be whether or not we actually know the standard deviation of the population or not. In order to do this, there's going to be a few different steps that's happening. We're going to learn about how to get that best point estimator for that population. We're going to calculate what we call a margin of error for confidence intervals. We're also going to construct those confidence intervals and basically determine the minimum size required for a survey or a sample that we need to do to meet this precision for the estimation. Understand that when you're looking at statistics, a major purpose of statistics is actually to provide information so that you can make an informed decision. Statisticians are normally asked to provide information about a variety of population parameters. Now, for example, this can be a television network. We may want to know how many Americans actually watch its TV shows each week. And this is very impossible to actually survey every single household. Yet, the network needs the best information available in order to make programming decisions. And because of that, this is kind of where inferential statistics plays an important role. Now, what we mean by inferential statistics, it's a branch of statistics that actually uses sample statistics and provides an estimate for the population. Okay, now for particular parameters, there are several sample statistics that can be used to provide estimates. And one of the things is that when we estimate for a population, there's a single value, and we call it our point estimator. Now, a point estimator, what exactly is it? It is a single number estimate of a population. Think of this point estimate as kind of like the idea of where we think something is going to be within a little bit of a range, okay? Now, the best point estimate for a population parameter is one that is unbiased. So an unbiased estimator is a point estimate that does not consistently underestimate or overestimate the population parameter. Now, there are three obvious statistics that can be used to estimate the population mean. And these are going to be your sample mean, your sample median, and mode. This is stuff that we've learned previously about. Now, it is actually not necessarily true of the sample modes and medians that their values will be the center about the mean of where the population is. Remember, we talked about earlier on if the data is skewed one way versus another, the mode and the median may not be in the middle, whereas the mean should be the average in the middle of all the data. Now, from the central limit theorem back in 7.1, we know that the mean of a sampling distribution of a sample mean is equal to the population mean, okay? Now, we did have some rules in order to apply the central limit theorem, but as long as it met those rules of the central limit theorem, we can take a sample and the sample mean is basically going to be the same as a population mean. Now, thus the sample mean does not consistently underestimate or overestimate the population mean, and it's actually what we call the best point estimator of the population mean. So therefore, that sample mean is an unbiased estimator for the population mean. So let's just start by finding the best point estimate for a population mean of a test scores on the standard biology final. And the following is a simple random sample taken from the population of test scores. Now, remind yourself we have a few different ways in which we can do this. We can do this by hand, or we can use our calculator. Now, one of the things I do want to notice if I'm going to use my calculator here, guys, do notice that none of these are just kind of raw data sent out here. So because it is just raw data itself, we are basically just going to put all of these in the calculator and then run a 1var stat. So let's do that. So remember, when we first start off with all of this, to put all this stuff in the calculator, we're going to start by hitting our stat button. we are going to then do edit because we got to put all the statistics in here. Now, the last couple of times we've been dealing with two lists. So remember, up, clear, and enter to clear out the list. Always clear it. Do not hit delete. If you hit delete, then you are going to get a lot of issues. And then just start typing in your numbers, okay? Okay, so we've got all of our stuff entered in there now. Now, double check. So do a quick double check. So you've got here, however you're entering them in, just kind of quickly go back and check. I do notice that I did put everything in. There was 30 items. If there is a typo, double check it right then and there. This shouldn't take too long in the sense of like when you check it. And if you're doing anything like this, do remind yourself that there was no like table list, so there wasn't a frequency list. So because there was no frequency list, it's just the raw data. We're just going to put it in list 1. You will notice I did not sort this from small to large. There's no reason to sort it because what we're going to do is we are literally going to hit stat, arrow over to calculate, and number 1 for 1 var stat. Now, this again is where my TI-83ers are going to be slightly different. So for my TI-84 plus CEs that are like me, or just a TI-84 that has this pop-up menu, remind yourself we didn't put anything in list 2. We didn't have a frequency list. So just delete that frequency list out and just make sure it says list 1 and click calculate. Okay. I do want to also point out for those of y'all that have the TI-83s, so you don't have that beautiful pop-up menu again. So what you want to do is you want to make sure to actually include list 1 only. Remind yourself that if there is 2 lists, we say list 1 comma list 2. Okay, and when you do that, remember the X bar is basically, that is our sample mean, our average. Now, if you were to do this by hand, do remind you that you are going to basically add up all the scores and divide by the number of scores there was, which is 30, which is going to be that 81.6, which is exactly what we got. Now, this is actually going to be our best point estimate for the population mean, which is going to be our sample mean, because it's kind of an unbiased estimator. The sample mean is kind of just what is pretty much the average of that sample. And since this is for the sample, it's going to be a great point estimator, meaning it's kind of a good guideline for what the population mean will end up being. Now, using only one value to estimate the population mean or any other population parameter leaves kind of a bit of room for error if you think about it. So in no fact, basically in no way of knowing that the likelihood that we've chosen the exact value, but we've probably gotten close. So what we're going to do is we're going to kind of give ourselves like, this is it, but it's got a little bit of a range. So plus or minus what we say, kind of a bit of a margin of error. So with that margin of error that we kind of talked about, we have a couple of things are going to have some new terminology. We're going to have this interval estimate. Basically, this interval estimate is a range of possible values for the population parameter. Think of this interval estimate as like plus or minus so much. So like normally like someone may say like the average is 80 plus or minus 2. That's what we mean by the interval estimate is technically it could be 78 or 82, but anywhere in between there we're good. And that's what we're going to be looking at. Now the level of confidence, and we're going to call that C just so you guys know, is the percentage of possible samples of a given size that will produce the interval estimate that actually contains that parameter. Meaning, how confident are you in this estimation interval? So if we add a level of confidence to our interval estimate, we now call it a confidence interval. It's basically an interval estimate associated with a certain confidence level. Now, a lot of these are going to have problems that are going to start saying a lot of different things in them. So the level of confidence is normally the letter C. They are normally given to you as a percentage. So if I say 95% confident, remind yourself we don't put 95% in a calculator, we always put 0.95. Now, if there is a 95% confidence, This does not mean that there is a 95% chance that the parameter falls within this interval, because a population parameter is a fixed value and it's either in the confidence interval or it isn't. So we can say that we are confident that this statistical method will result in 95% of all possible interval estimates contained in this true population parameter. Okay, so think of that as something like, say we have a 90% confidence interval for our mean from 10 random samples. So out of these 10 samples, you guys can see here that out of the 10 samples, 1, 2, 3, 4, 5, 6, 7, 8, 9 of them actually contain what the mean is. But 1 out of that 10, so 9 out of the 10 worked, but there's at least 1 out of the 10 that it didn't actually fall in there. It got really close, but the mean is not actually in the middle, or even contained within that interval itself. Okay, so basically in the long run, we can kind of say that if I'm 90% confident, 9 out of 10 of our samples will actually contain the actual population mean within that plus or minus interval that we have. So how do we actually find this confidence interval for the population parameter? Now, obviously the confidence interval will have to be constructed around what we call our best point estimate, in which we can find our unbiased estimator. And how big do we actually make this interval? Like how much do we add or subtract? Well, this is what we call the margin of error. The margin of error is the maximum error for the estimate. Okay, it's the largest possible distance from the point estimator that will allow our confidence interval to cover. Okay, so when we talk about this, remind yourself that the point estimator is going to be smack dab in the middle, and then we're going to subtract our error and add our error. This is kind of that whole like plus or minus so much. So to construct our confidence interval, the most common population parameter that we have is basically subtract that margin of error and add it from whatever that point estimator is. So how do these problems look? And you're going to start to see these problems are going to be very, very wordy. And we got to pull out some good key information out of them, okay? So a college student researching study habits collects data from a random sample of 250 college students on her campus and actually calculates that the sample mean, also known as X bar, is 15.7 hours per week. Now, if the margin of error for her data using a 95% level of confidence is E equals 0.6 hours, we want to construct a 95% confidence interval for her data. And then we're going to interpret it. So notice I've highlighted some very important key things. Okay, now not everything that I've highlighted is going to be used here, but what is going to be used is we need to basically find our point estimator, whatever that might be. Okay, so we're going to take that point estimator and we are going to add and subtract our margin of error. Okay, because we got to basically figure out what our interval is. We have to have a low and a high when we talk about intervals. Okay, so the best point estimator for a population mean is going to be a sample mean. Okay, so we're going to take that sample mean of 15.7 to be the point estimator for the population. And we're going to give that, we were actually already given our margin of error. They told us our E was 0.6. So basically, I'm just going to take that 0.6 and we are going to add it and subtract it to be able to find our interval itself. Okay, so to get the lower endpoint, we're going to subtract the margin of error from the sample mean. That is basically X bar minus E. Okay, and that's going to be 15.7 minus a 0.6, which is going to give me 15.1. Now to get the upper part of it, we're going to add the margin of error to the sample mean, so basically X bar plus E. Thus, basically, we end up with our upper endpoint, which is 15.7 plus 0.6, which is a 16.1. Okay, so I have my low and I have my high, and we're basically 95% confident. because that's what they told us. So therefore, our confidence interval ranges from 15.1 to 16.3, and our confidence interval can either be written in a mathematical inequality symbol statement or interval notation. Now, if I am going with inequality symbols, it's going to be 15.1, which is less than mu, which is less than 16.3, which means basically mu is contained, or the population mean is contained within these. Or if we're using interval notation, so this is kind of a little bit more kind of like algebra-y, the way that we actually write stuff. You're going to say your lower bound, comma, your upper bound, and just put parentheses around either side. This right here, just so you know, this is not an ordered pair. Okay? Very important to remind yourself, this is not an ordered pair. This is basically an interval. Okay, so how would I actually write that in words as well? So the interpretation of our confidence interval is that we are 95% confident that the true population mean for the number of hours per week that students on this campus spend studying is between 15.1 and 16.3 hours. Now, constructing a confidence interval for a population mean is not complicated when you're actually given that margin of error. All you have to do is basically add the margin of error to and subtract it from the point estimator, okay? But what if you aren't given the margin of error? How can we actually calculate it? Now, calculating the margin of error requires choosing the right distribution or advanced statistical techniques. Now, this is where we had to kind of talk about Chapter 7. Now, according to the central limit theorem, when the following conditions are met, the standard normal distribution can be used to calculate the margin of error of a confidence interval for population mean. All possible samples of a given size have an equal probability of being chosen. So basically, we have a simple random sample is being used. We do actually have to kind of know what this population standard deviation is. So do we actually know that? And then either the sample size is at least 30 or the population distribution is approximately normal. Now remember that this last one here that we talked about, so this one here, this was basically our main idea for the central limit theorem. As long as it met kind of these conditions here for it was at least size 30, and we if we didn't have a size 30, we knew that it came from something that was approximately normal. The central limit theorem can be applied. But all of the ones that we talked about in Chapter 7 is I had already given you the population standard deviation. It was kind of known. So now we have to figure out, is it actually known to be able to do this interval? Now, the level of confidence, we're going to call it C, like I said, it's going to correspond to the area under the curve, but the area under the curve, do understand it's going to be centered about our population mean or our point estimator, which is X bar. So if we're 95% confident level, we basically need to find Z values that correspond to this middle area to where there is a 0.95 area around that standard normal distribution. Now, these Z values that are going to kind of mark the boundary area for the C under the middle of that standard curve, normal curve, we call these critical Z values, and they're basically denoted as a negative Z alpha over 2 and a positive Z alpha over 2. Now, where the hell does alpha come from? Well, understand that if the area under the curve basically is considered to be C, okay, that's our confidence level, then the total area in the two tails is going to be 1 minus C, and we call that value alpha. So it's basically alpha is our complement of C itself. Now, because we are talking about it in terms of, guys, do remind yourself that we are basically saying that, and kind of draw a little curve here. So here's our kind of X bar. We're saying that here is going to be 95%. Well, what is going to be here and here? Okay, so this is C. this is going to be my alpha divided by 2. So we know alpha in our case here will be 5%, but this is going to be 5%, but half of it's going to be here, and this is going to be the other 5%, but half of it is going to be there. So this is where we get that alpha over 2, okay? So it will tell us kind of the area for one tail itself. Now, because of this, the notation for z alpha over 2 indicates that critical value, z value that corresponds to that area. Basically, we've got a right tail and a left tail, but again, we kind of want it perfectly symmetrical. So the critical value to the left end of the area for the curve is going to be the -1, which is going to be that negative z alpha over 2. We do kind of prefer to use this one when using only the tables. If you're trying to still work your way through this with the tables, you're going to be using the negative z alpha over 2. Okay. Now, the critical value is based only on the level of confidence. So, and it's not actually based on the sample size itself. Your sample size will change based upon what your population is going to be. But the confidence interval itself, that z is going to change based upon that. So if we are looking at a 95% confidence interval, that's going to remain the same for every problem for which is appropriate to use the standard normal distribution. But sometimes we might look at it and it might be like, oh, I want to be 90% confident, or I want to be 80% confident. Okay, so the last one we talked about was 95% confident. And pretty much we are going to look a lot at very similar ones, but do understand that they do change based upon what problems we're looking at. These are some commonly used levels of confidence, depending on what your problem is itself. Majority of the times in most statistical speaking, just so you have an idea, we do actually try to keep it somewhere in this range here for being statistically significant. Does it always have to be that way? No, depending on how much information you know, you might actually go to a little bit lower level of confidence. But most most decision-making ideas, if you're talking about statistics, we do try to keep in this level, but I have seen some go as far down as 80% confidence level before. Okay. So, and kind of just to give you guys an idea here, I mean, I know this is a lot of information that you are looking at, but keep in mind that if I have this confidence level here of 80%, my alpha is going to be 20%, and then half of that, so will be basically 10%, and I'm looking for the z value for that 10% area. So these are the z values that correspond to these alphas. Now, how do I calculate the margin of error of a confidence interval for where we actually know the population standard deviation? Now, this will change based upon whether or not I know the population standard deviation or not. So kind of make yourself a note of this. And I am sorry to say that there is not a very nice like calculator, just type in this information and then it spits back out your E. There is a way to use your calculator to kind of help you figure out what E is going to be, but it involves a lot more work. So you definitely want to make note of this down here. You want to write it down somewhere because you are going to want to know this E. And do understand that, guys, this is basically our formula here is only if you actually know the population standard deviation. Okay, and it meets the following conditions of at least 30, or it was approximately normal to begin with. We'll look at some things that are not later, but kind of get this idea down. So basically our E is going to be, we have to get our Z value, which is basically our Z alpha over 2. So we need to know that Z value, and then multiply it by the standard deviation of the sample means, which again, we just learned about this in chapter 7, which is basically the population mean divided by the square root of n. Okay. Now again, remind yourself that that Z alpha over 2 is basically coming from our confidence interval. You don't actually normally know what your alpha is. They normally tell you your C instead, but you do have to kind of know your sample size to begin with, and you have to know the population standard deviation. So let's kind of look at how a problem's going to look for this. Researchers want to estimate the mean monthly electric bill in a large urban area using a simple random sample of 100 households. Now, assuming that the population standard deviation is actually known to be $15.50, find the margin of error for a 99% confidence interval. We're going to round our answers to 2 decimal places. Again, I'm going to highlight some keywords here. We know that we have a random sample of 100 households. Okay, we know that our population standard deviation is $15.50. We want to have a 99% confidence interval, and we want to find that margin of error for this confidence interval. Okay, so knowing all of that information, remind yourself that basically to get that margin of error, we're going to have to get our Z alpha over 2 times our population standard deviation divided by the square root of n. Okay, so the first thing to get that Z alpha over 2, well, first of all, we got to remember what our C is. So our C basically was 99%, so 0.99, which means our alpha is going to be 0.01. And again, remind yourself how you actually get that is not as hard as it looks. Everything always adds to be 1. So alpha is always going to be 1 minus C, which in our case is basically 1 minus 0.99, which is where I'm getting my 0.01. Now, to get the critical value, that Z critical value, we're going to basically take this and divide it by 2. So we're looking for our Z alpha over 2, which is basically our 0.005, which is this right here is literally just alpha divided by 2. And this, ladies and gentlemen, if you look at either the table that's already pre-done, which has got it there for you, or you can use your calculator to help you out here, and that's going to be this here. Okay. And the other things we had to make note of was our population size, which was n equals 100, and our standard deviation, which was $15.50. Now, the central limit theorem is going to apply because we have a population, we have a sample size out of the population that is bigger than 30. Okay. So substitute the values in. So basically we have a 2.575 times 15.5 divided by the square root of 100, which is going to give me 3.99125, which basically, if you round to 2 decimal places like they said, our margin of error is going to be $3.99. So we're going to take whatever that point estimator is and basically add or subtract out $3.99 to get that confidence interval. Now, at this point here, they haven't told me what that is, and that's our next step. So to construct our confidence interval, we actually have to figure out what that E is, and then we take our point estimator and we add and subtract out our E. Okay? So in order to estimate the number of calls to expect at a new suicide hotline, volunteers contact a random sample of 35 similar hotlines across the nation and find out what the sample mean is basically 42 calls per month. Now we're going to construct a 95% confidence interval for the mean, number of calls per month, and we're going to assume that the population standard deviation is known to be 6.5 calls per month. Okay, so step 1, as we look through all of this, is what was that point estimator? Now, I don't actually have to go looking hard. They actually told it to me. They basically said that when we looked at this to get a confidence interval, we need to know our point estimator and the margin of error. And the point estimator is literally the sample mean. That is all it is. In our case here, they said that the sample mean was 42 calls. Okay. So now step 2 is going to be go find that margin of error. And in order to do the margin of error, remind yourself we actually have to know our population standard deviation. Now, you also have to know what your confidence level was. So in our case here, again, they told us that we are going to be confident by 95% confident. So I'm going to basically take my alpha is going to be 1 minus 0.95, which is where I get a 0.05. I'm going to get my alpha over 2, which is just basically that 0.05 divided by 2, which is where I'm getting my 0.025. And now we have to find the z value that is that item, okay, which in our case is going to be a 1.96. Okay, so now that I know my critical value, I need to know what my population standard deviation was and the sample size and put it all in the formula. So substituting into that formula, we're going to take that z alpha over 2, which is 1.96, times 6.5 divided by the square root of 35, which is approximately 2.153453. Okay. Do understand, take this as an unrounded, like take a bunch of decimals on this at first here. So take all of these decimals, because my final answer was the actual interval itself. So you want to take as many decimals as possible before you go to this next route here. Now, if you're a little unsure how I'm getting this part right here, this z alpha over 2, everybody figured out where I got the alpha over 2 from, but my z part, you can look at the table, which is in 8.1. I highly recommend that, or you can use your calculator to help you out with that. Okay, so a quick way for the calculator to help us out here, I'm going to clear this out. To get any z value, so basically remind yourself that when we were looking for a value underneath, we used inverse norm. So if I just take this item here, which again, remind yourself, we're taking that as our alpha divided by 2. Okay, anything that z always has a normal distribution shape, but the mean itself is 0, the standard deviation is 1. We're just looking at our left tail there. Okay, and again, I'm just going to hit enter. And guys, this is where I got that negative 1.96. We are going to assume it's positive. And the reason why, again, I'm saying assuming it's positive here, because this one's going to be positive, this one's going to be negative. So eventually we're just going to end up subtracting it anyway, so we don't have to worry about the positive or negative side of it. We just take that value there and multiply it by 6.5 divided by the square root of 35 there. Again, take as many decimal places as you can. Most of the time your z values will be slightly already rounded, so be aware of that. And then the last step is actually to get that interval itself. So I'm going to take that point estimator, which we said was 42, and I'm going to subtract that 2.153453, which is going to be 39.8. And then I'm going to add it, so 42 plus that 2.153453, which is about 42.2. And there we go. So therefore, we are 95% confident that the interval ranges from 39.8 to 44.2 calls per month. And that's basically what our interval itself is going to be. Again, there are two different ways to write it by shorthand, which is 39.8, which is less than our mean, which is less than 44.2, or I can write it in the interval notation, which is parentheses 39.8 comma 44.2, closing those parentheses. If I were to write it in a sentence, the interpretation of our confidence interval is that we are 95% confident that the true population mean for the number of calls to a suicide hotline across a nation are between 39.8 and 44.2 calls per month. Okay, let's try this again. And again, the more we try this, the more you guys are going to see that there's pretty much everything is given to you in the problems, but you just kind of have to find and read for it. So we've got our toy company wants to know the mean number of new toys per child bought each year. Now, marketing strategist at a toy company collects data from 1,842 randomly selected children. So the parents tell this, okay, so this is basically N here. Now, the sample mean of the sample is found that there's about 4.7 toys per child. We want to be 90% confident interval for the mean of the new toys per child purchased each year. Okay, and we are going to assume that the population standard deviation is known, and we are going to let that be 1.9 toys per child per year. Okay, so all of that information there, guys, straight away, this is N, this is basically my X bar, this is my C, and there's my standard deviation. So we already know what our point estimator is. Our point estimator is that X bar, which is 4.7. Our margin of error, we needed to know what our C was, which is 90%. So my alpha is going to be 10%. But again, remind yourself, we are always going to be dividing it by 2. Okay. And from there, guys, do remind yourself that basically once you have that, we are literally going to find that Z value that's associated with it. And I highly recommend looking at the table. And that table is, which is like table, I think it's 8.1, which is 1.645. Okay, now we just basically have to find the rest of our margin of error. So using that formula, our Z alpha over 2, multiplied it by the population standard deviation divided by the square root of N, which is going to give me 0.072824. Again, take all of those decimals. Do not round. If you round right here, you're going to get it wrong. So make sure you take a ton of decimals before you do this next step. Okay, and you're going to take, last step is basically find your lower and your upper. So you're going to take your X bar minus your E, and then you're going to take your X bar plus your E, and we basically have our answer there. We are 90% confident that the true population mean for the number of new toys per child bought each year is going to be between 4.6 and 4.8 toys per child. Now, again, do remind yourself, this doesn't mean that the kid is getting 4.7-ish toys. It's basically that the kid can get 4, the kid could get 5, but when I look at a sample, that sample average for the population is going to end up being about 4.7 or 4.6 or 4.8. It's going to be in that range value. Okay, so let's try this again. So the owner of a local company that produces hand-knitted socks wants to know, for women in the area, the average length of a woman's foot from toe to heel. Now, we basically are going to collect our data from 431 randomly selected women. The sample mean is found to be 8.72. We're going to construct a 95% confidence interval for the mean length of a woman's foot in the area, and we are going to assume that we actually know what the population standard deviation is, and it's 0.36 inches. Now, I'm actually going to show a slightly different way here. So to help you out, all I'm going to do is pull out these key information things, and I do want to have all that key information there. So we collected 431 randomly selected. We know that our sample mean was 8.72. We know that we were 95% confident. And we also know what the population standard deviation is. Okay, all of this was in the problem previously, and I wanted to know all of this because, and again, this is where everything's coming in, I can actually use a calculator if I am looking for a confidence interval. So remind yourself that in this problem in particular, it says to construct a 95% confidence interval. So I'm not asking for what the margin of error is. I actually do want to know what the confidence interval itself is. Now, if you are using a confidence interval, we can actually use our calculator to help us out. The calculator will not give you E. Or I got that. The calculator will not give you E. What the calculator will give you is the interval. Now, this is where I said, like, technically the calculator doesn't give you E, but you could work your way backwards. That is a possibility. But the calculator itself will never, ever give you E. It will never give you that critical value without a little bit of extra work. So for a TI 83 or 84 calculator, the first thing you're going to do is actually hit Stat. And this is going to be a little bit new for you. So let's do these steps to kind of help you out here. Okay, so everybody should see my beautiful calculator up on screen. So I'm going to clear out. I always want to start with a fresh, clean home screen. So make sure this is clear, especially my TI 83ers. It's very important to have a clear home screen here. And then click Stat. Okay. Now, we've always just done stat edit, or we've done stat calculate and done one var stat. I actually want you to scroll all the way over to test, and you'll notice in test, somewhere down here, I think it's number 7. Yeah, number 7. It says Z interval, because we're looking at a confidence interval, but we're looking at a confidence interval for Z values, things that you actually know the population standard deviation. So choose number 7. Okay, now there's going to be 2 options. One is data and one is sets. Now, if you actually have data given to you, you're going to use the data. But in this case here, they didn't give me any raw data. They actually gave me the statistics itself. So I'm going to scroll over, highlight stats, and hit enter to execute that. And then what was that population standard deviation, which was at 0.36. They also told us what X bar was, which was at 8.72. We know that our sample size was 431. Okay. And what was the confidence level we wanted to be, which in our case here was a 95% confidence, so 0.95. Now, once you've got all the stats selected and put all those stats in, again, these are the 4 things that I was highlighting in the problem itself. We're just going to click calculate, and we should be given something that looks like this. Okay, so once you highlight, calculate, and press enter, basically this is your answer. Like literally right there is your beautiful answer. You don't actually have to do any more extra work. It's right here. Again, this is the interval itself. Notice it does not give me E. So ladies and gentlemen, this is where if you have to go find your E, if it's a multi-step problem, you have to go find E, you have to go about this a slightly different way, okay? So, but here we have it, and basically that's our answer. So therefore, we are 95% confident that the true population mean for the length of a woman's foot is between 8.69 and 8.75 inches. Okay, so let's just look at interpreting some of these confidence intervals a little bit. So we have a new study, and it's comparing the sensitivity to HIV home test to a professionally administered home test, professionally administered test versus a home test. That basically they're the same testing procedure. We are going to measure the test sensitivity, representing the percentages of results that are correctly labeled positive when HIV is actually present. Now we have a table that shows a 95% confidence interval for both of the sensitivities of the test. Okay, so for the home test, for a sensitivity for a 95% confidence interval, so we're 95% that the sensitivity is 95% confidence that the sensitivity for a home test is between 86.6% and 96.9%. We are 95% confident that for a professionally administered test, the sensitivity rating is between 95.85% and 99.08%. And guys, these are actually true sources from a publication back out of the 16th of May, 2012, okay? So based upon this, which of the following statement provides the most unbiased interpretation of a confidence interval? We can say either A, professionally administered tests were found to be far more reliable with 99.08 sensitivity than the home test with an 86.6% sensitivity. Or we can say home test methods for HIV are just as sensitive as those administered professionally. In fact, they are even more sensitive since they have a possible 96.9% sensitivity range compared to the 95.85 for the professional one. Okay. Now, I want to kind of talk about how the second one here. Home testing is just as sensitive as those administered professionally. Guys, if you think back to this one here, a home test had this range between here and here, whereas this is the high level of its sensitivity, whereas the professional one went from 95 to 99. So it seems like the professional one is a little bit more sensitive. Okay. Now with option 1, as well as we talk about this here, it says the professional administered tests were found to be far more reliable with a sensitivity of 99.08 than the home test with an 86.6 sensitivity. Okay, first of all, you're comparing a lower to an upper. Can't do that. You can't compare a lower to an upper. Like, that doesn't even make sense there. Okay, so even though, and the last one was comparing an upper to a lower. So like neither one of these items that we're talking about here even makes sense in the probability of what we're talking about. So let's look at our third option. Is basically the results provide reasonable assurance that the home testing is as effective as a professionally administered test. Now, out of all three of these, option 3 is going to be the best interpretation of a confidence interval given. Both confidence intervals actually slightly overlapped if you looked at it. So it is possible that both tests have the same sensitivity rating. Therefore, it's kind of a similar way that we can talk about it. This fact is, in fact, that like when you're looking at things that overlap like that, a home test versus a professional one, a part of those findings that an expert panel reported to the FDA here will look at, that's what they're kind of looking for is a home test. Can you get that same average rating that could be possibly found in a professional setting for cheaper cost? Okay. So the last thing we need to talk about is what about the minimum size of a sample? So a lot of the time, suppose that a researcher actually wants to conduct a statistical study, but they want to have a high level of confidence, meaning that the margin of error that they have is going to be relatively small. Now, with that, basically by using a large sample size, the estimates are based on more data, and this results in an increased level of confidence without actually increasing the margin of error. So a logical question would be basically how large of a sample does he actually need to give this confidence level? The answer to that is going to depend on the level of confidence and the margin of error that they plan on using. Now, it would be nice to have a large enough sample with like thousands and thousands of data, but time and money will usually prevent one of these such luxuries. So basically, what is the fewest number of data values that you must collect to make some desired level of confidence within a particular margin of error? So basically, a lot of times this is going to be, what is the minimum size of sample that we need for our requirement? Now, this is actually a formula that we've already seen before, so this is actually not a new formula, but it is one, it looks a little bit different in the way that we've written. So I do want to kind of bring your idea of here where this actual formula comes from. So remind yourself, we were talking about our margin of error was basically E equals, okay, and that was our Z alpha over 2, and we took that times our population standard deviation divided by the square root of n. Now, if you actually were to take this item here and solve for n, you would get this formula up here. So you would probably want to make sure to make note of these two and understand the difference between them. E is going to calculate out your margin of error. The one solved for n is going to give me the minimum sample size I need to get a certain margin of error. Now, in order to use this one here, you must know what E is. In order to do this one here, you must know the sample size. So it's slightly different here. And normally, again, these are going to be kind of based upon things that we've looked at previously in problems. So we're going to kind of take a peek at this. Okay. And again, remind yourself that Z alpha over 2 is going to come from our critical value that we know. And again, alpha is always going to be 1 minus our C value. That's going to what our alpha actually is. And we do need to divide it by 2 because we're looking for an interval, meaning an upper and a lower value. Okay. But again, this is all with the population standard deviation is actually known. So knowing the population standard deviation is very, very unlikely. So do understand that we must determine a way to estimate the population standard deviation. Now, one of those methods to use that would be our sample deviation as a point estimator for the population standard deviation. And we can also use an estimate of a population standard deviation for a similar study on the population, or a pilot study on that population as well. Now, another method is basically if the range of the population is actually known, is to divide that range of the population by 6 and using this value to kind of estimate the population standard deviation there. Do understand that when calculating our minimum sample size, remember that we're basically trying to determine the number of data values we need, which is going to be a whole number. Now, this is really important, and this is kind of where a lot of people make a mistake on this here, is basically, and kind of make note of this, is in this formula, I don't care what the decimal value is, you will always, and again, no matter what, you will always round up to the next larger number. Okay, it's very, very important that you do that. Okay, so remember that the minimum size that a sample has to be is if I ended up with, say, something of, we get n to equal, say, 153.2, I automatically have to say 154. Okay, you always have to meet that minimum value, which basically I needed that extra 0.2 of a person, so I have to go ahead and round up. Okay, so we should always try for samples, if possible, always making sure that round up option there. Okay, so let's actually put all that stuff into play, because I know that's a lot of words and trying to figure that out. So determine the minimum sample size needed if we wish to be 90% confident that the sample mean is within 2 units of the population mean. Okay, and we're going to estimate for the population standard deviation to be an 8.4 is available from a previous study. So we've done a previous study and we say that the population standard deviation is basically estimated to be 8.4. So we're just going to let that roll as our population standard deviation. Okay, so the first thing is that from all this information given, we are finding our key ideas here. So they said we want to be 90% confident, so that's basically my C value. They told me that we're going to use this 8.4 as our population standard deviation. Now, they also said, and this is kind of where a lot of people get a little messed up, E is equal to 2. Now, this is not normally given as a number. Sometimes this is written as words. So the phrase within 2 units of the population mean basically is telling us our desired maximum margin of error is that it has to be within plus or minus 2. Okay, so now that we know all that information, we are going to say that we're 90% level of confidence, which means that I have got a 10% alpha value there. And since I have a 10% alpha value, I'm going to take that and divide it by 2. This is where this is coming in, which is our Z is 0.05. Again, you're going to either use your table or you are going to use the calculator to get this 1.645. And then once you have this, you can now plug everything into the formula, which is our Z alpha over 2, which is the 1.645 times the 8.4, our population standard deviation, divided by E here, okay? And then take all of that, make sure the parentheses goes around all of it and square it, which is about 47.78. And again, I do not care what this is. Whatever this is after the decimal here, always round up, which will be 48. So basically what that says is that the sample size, in order to construct a 90% confidence interval that the population mean will be within that desired margin of error of plus or minus 2, has to be at least 48 in our sample size.